Hello students, a very good morning. Myself Virendra Kumar Maurya. My topic is three-phase faults. Electrical fault. What is the definition of electrical fault? The fault in the power system is defined as the defect in the power system due to which current is distracted from its intended path. Faults in the power system may occur because of the number of natural disturbances like lightning, high-speed winds, earthquake, etc. It may also occur because of some accidents like falling off a tree, vehicle colliding with the supporting structure, and aeroplane crashing, etc. Faults in the power system is mainly categorized into two types. They are open circuit fault and second one is short circuit fault. These faults are further categorized. Now the number one, that is open circuit fault. It is categorized as one conductor open, two conductor open and three conductors open. Now the number two, that is short circuit fault. Short circuit fault is further categorized as symmetrical fault and unsymmetrical fault. Symmetrical fault as three-phase short circuit fault and three-phase to ground fault. Now in the case of unsymmetrical fault, it is single line to ground fault, double line to ground fault, and third one is line to line fault. Now see all the faults in detail. Now the number one is open circuit fault. What is the definition of open circuit fault? The open circuit fault mainly occur because of the failure of one or two conductors. The open circuit fault takes place in series with the line, and because of this it is also called a series fault. Such type of faults affect the reliability of the power system. In the open circuit fault, one conductor open is shown over here. This one is the first one. See the first phase, that is the red phase, that one is open. So current is interrupted. Such type of fault is known as series fault in one conductor. Now see the two conductor open fault. In this type of fault, two conductors or two phases are open. It may be any two phases in between these three. It is red and blue, blue and yellow, yellow and red. Current is interrupted by two conductors, so it is known as two conductor open fault. Now see the third one of open circuit fault, that is three conductor open fault. In this type of fault, there is only one combination. All the three phases are open, all the three conductors are open. That's why it is known as three conductor open fault. It is one of the series fault. Now see the short circuit fault in three-phase power system. In this type of fault, the conductors of the different phases come into the contact with each other with a power line, power transformer or any other circuit element, due to which a large current will flow in one or two phases of the system. This large current is used for determining the rating of circuit breaker. Now see three-phase short circuit fault, which is a symmetrical fault. See the diagram very carefully. Here all the three phases are short circuited. That's why it is known as three-phase short circuit fault. But system remains balanced. That is, the system remains symmetrical even after the fault. The line fault occurs rarely, but it is the most severe type of fault which involves the largest current. Now see the next one, that is three-phase to ground fault. In this type of fault, all the three phases are short circuited along with ground. The probability of occurrence of such type of fault is nearly 2 to 3%. Now see the second type of short circuit fault, that is unsymmetrical fault. In unsymmetrical fault, different current will flow in the different phases, that is current differing in magnitude and phases in the three phases of the power system, as known as unsymmetrical fault. In the unsymmetrical fault, the first one is single line to ground fault, as it is clear by the picture that single line to ground fault occurs when one conductor falls to the ground or contact the neutral conductor. The 70 to 80% of the fault in the power system is the single line to ground fault. Now see the second unsymmetrical fault, that is double line to ground fault. It is clear by its diagram that in double line to ground fault, the two lines come in contact with each other along with the ground. The probability of such type of faults is nearly 10%. Now the next unsymmetrical fault, that is the third one, is line to line fault, as it is clear by its diagram that a line to line fault occurs when two conductors are short circuited. The major cause of this type of fault is the heavy wind. The heavy wind swinging the line conductors, which may touch together and hence causes short circuit. The percentage of such type of faults is approximately 15 to 20%. Now see effects of electrical faults. We have been discussed so many faults over here. Now see their effects. Number one, that is over current flow. So when the fault occurs, it creates a very low impedance path for the current. This results a heavy current is drawn from the supply and make the condition of overcurrent. After overcurrent flow, the next one is loss of equipment. See it very carefully. Heavy current will flow through the equipment due to the short circuit, which leads to improper working of equipments or devices. Sometimes heavy fire causes complete burnout of the equipment. Now see the effect of electrical faults in interconnected active circuits. Faults not only affect the location at which they occur, but also disrupts the active interconnected circuits to the faulted line. Now the next one, that is danger to operating personnel. Fault occurrence can also cause shocks to individuals. The severity of the shock depends on the current and voltage at the fault location and even may lead to death. Now, in the series of effect of electrical faults, the next one is electrical fires. Short circuit causes flashovers and spark due to ionization of air between two conducting paths, which further leads to fire, as we often observe that in news such as building and shopping complex fires. Keeping in mind regarding electrical faults, we are going to use some limiting devices known as faults limiting devices. With the help of fault limiting devices, it is possible to minimize causes like human errors but not environmental changes. Fault clearing is a crucial task in the power system network. If we manage to disrupt or break the circuit when a fault arises, it reduces the considerable damage to the equipment and also property. Some of these fault limiting device includes fuses, circuit breaker, relays, etc. And we are going to discuss these devices one by one. Fuse is the first line of defense in electrical faults. It is the primary protection device. It is a thin wire enclosed in a casing or glass which connects two metal parts. This wire melts when excessive current flows in the circuit. The type of fuse depends on the voltage at which it is to operate. The manual replacement of the wire is necessary once it is blown out. The second one is circuit breakers. Circuit breakers are used to disconnect the faulty portion from the healthy one. It causes automatic tripping of the circuit when a fault occurs. It can be electromechanical circuit breakers like vacuum circuit breakers, oil circuit breakers, or ultra fast electronic circuit breakers, etc. And the next one is relay. It is a conditional based operating switch. It consists of a magnetic coil and normally open and closed contacts. Fault occurrence rises the current which energizes the relay coil, resulting in the contact to operate, so the circuit is interrupted from flowing of current. Protective relays are of different types like impedance relay, Moore relay, distance relay, etc. Now the next one is lightning power protection devices. It is used for the high voltage protection. These includes lightning arrestor and ground devices to protect the system against the lightning and surge voltages. Now see the numerical. Here some data is given for the three phase, that is 400 volt, 50 hertz. These are the data for the supply, and the power consumption by the load is 1.5 kilowatt. With a power factor it is 0.2 lagging. Calculate resistance, inductance of each coil. Resistance and inductance of each coil. This is our target. And load is star connected. First of all, this 400 which is given to you, it is VL. VL is equal to 400 volt. That's why we can calculate phase voltage. In the case of the star, it is BL divided by under root 3. That's why it is 400 divided by root 3. It becomes 231 volt. Right? Power which is consumed by the load is 1.5 kilowatt. Power formula for the power is P equal to under root 3 BL IL cos phi. Right? So power, that is 1.5 into 10 की power 3 under root 3 into BL. It is 400 into IL, and the value of the cos phi is 0.2. With the help of this equation, we can calculate the IL, that is line current. It is 10.83 ampere. And in the case of the star, line current is equal to the phase current. So the value of the phase current is also same, that is 10.83 ampere. Now we can calculate ZPH, which is nothing but BPH divided by IPH. BPH, that is 231. IPH is same, that is the 10.83. Right? It is 21.33 ohm. This is the value of ZPH. Right? And the cost component of this ZPH is nothing but RPH, which is required over here. RPH is nothing but ZPH into cos phi, that is 21.33 into 0.2, it is 4.27 ohm, it is RPH. Right? Resistance part of the load. Now for the calculation of L, first of all calculate XPH, which is nothing but square of ZPH minus square of RPH with square root, that is 21.33 minus 4.27 with the square root. After the calculation, it is 20.9 ohm. Right? Now LPH, which is nothing but X HPH divided by 2 pi F. Okay, it is 20.9 divided by 2 into 3.14 into 50 hertz, which is given over here. Right? And it is 0.0665 Henry. Right? I am repeating. Please see the question very carefully. There is a star connected load which consumes power 1.5 kilowatt with the 3-phase supply. Data for the 3 phase is 400 volt 50 hertz and power factor is 0.2 lagging. In the case of star connection, this voltage is considered as line to line voltage, that is line voltage. With the help of line voltage and phase voltage relation, that is BPH equal to BL upon root 3, we can calculate the phase voltage. And the formula for the power consumption is same in star or delta, that is P equal to root 3 BL IL cos phi. With the help of this equation, we can calculate the value of IL. In the case of the star, the value of IL is nothing but value of IPH, which is 10.83. After that, BPH and IPH, we can calculate ZPH, and the cost component of the ZPH is nothing but R, which is And according to the question, calculate resistance and inductance of each coil. Just by this the value of R. With the help of RPH and ZPH, we can calculate XPH, and with the formula of L is equal to XPH divided by 2 pi F, we can calculate L, that is 0.0665 Henry. Now see the next. Now according to the question, data for the three-phase supply is 440 volt and 50 hertz. Current which is drawn by the source per phase is 30 ampere, and it is star connected load. Now calculate resistance, reactance per phase, reactive power and power factor. So this one 440 volt is the line voltage. It is 440 volt. So according to the relation of BPH and BL, we can calculate phase voltage, that is 440 divided by root 3, it is 254 volt, right? According to the formula of power, that is power per phase equal to BPH IPH cos phi. So cos phi is equal to power, that is 6 kilowatt divided by BPH, that is 254 into IPH, and IL are same. So in the place of IPH it is 30, and this one is the power which is given by the wattmeter. So power is given over here 6 kilowatt. After the calculation, right, cos phi is calculated over here, it is 0.787. For the value of ZPH, it is BPH divided by IPH. BPH is 254, IPH is 30. With the help of these two, we can calculate ZPH, that is 8.47 ohm. Now see the first part, that is RPH. RPH is nothing but cos component of ZPH. So it is ZPH into cos phi, that is 8.47 into 0.787. RPH is 6.66 ohm. Now the XPH, it is the second part, reactance, ZPH into sin phi, it is 8.47 into sin phi. Sin phi is 0.616. We can calculate the value of sin phi with the help of square root of 1 minus cos square theta. It is 5.22 ohm. Now the reactive power, that is the third part, reactive power Q is equal to root 3 BLIL sin phi. It is under root 3 BL, it is 440 into 30 into sin phi, that is 0.616. After the calculation, it is 14083 volt ampere reactive. And this one is the cos phi, this will be the fourth part, 0.787 lagging. Now according to the question, the value of resistance is 5 ohm and inductance, that is 0.02 Henry. Such type of three similar coils are connected in delta to a supply 440 volt, 3 phase and 50 hertz. Calculate line current and power absorbed. I am repeating the question. Three similar coils having the resistance 5 ohm and inductance 0.02 Henry are connected in delta to a supply having voltage 440, 3 phase and 50 hertz. Calculate line current and power. Okay, first of all calculate XL, which is nothing but 2 pi FL. 2 pi F and L. After this it is 6.28 ohm. Okay, with the help of XL and R we can calculate impedance per phase, right? According to this formula, it is square of 5 plus 6.28 square with the square root, it is 8.05 ohm. Now we can calculate power factor, that is cos phi, which is R upon Z. R is 5, it is 8.05 and it is 0.622 lagging. This is the value of power factor. According to the question, they are delta connected. So BPH is equal to BL, that is 440 volt. Now calculate current per phase, whatever the voltage divided by impedance per phase. 440 divided by 8.05. So the current per phase is 54.6 ampere. And the line current, according to the delta, it is under root 3 times of IPH, under root 3 times of 54.6, that is 94.8. This is our first part. This one. Now power absorbed. P equal to under root 3. Now see the second part, that is P equal to under root 3 BL IL cos phi equal to under root 3 BL is 440, IL is 94.8 and the cos phi it is 0.622. After the calculation it is 45,000. Now see the question in overall. Three similar coils each having a resistance of 5 ohm and inductance 0.02 Henry are connected in delta to a supply 440 volt, 3 phase and 50 hertz. Calculate line current and power absorbed. First of all, I am going to convert L as a XL, that is inductive reactance. By the formula XL is equal to 2 pi FL. The value of XL is 6.28 ohm. With the help of XL and R, we can calculate impedance per phase, that is ZPH, and it is 8.05 ohm. With the help of R and ZPH, we can calculate the power factor, and it is 0.622 lagging. In the case of the delta, line voltage and phase voltages are equal. So the value of the phase voltage is equal to the line voltage, that is 440 volt. We can calculate phase current with the help of BPH and ZPH, and it is 54.6 ampere. In the case of delta, line current is under root 3 times of the phase current. This is our first part. and IL is equal to under root 3 times of IPH, that is 54.6 into root 3, it is 94.8. Line current is 94.8 ampere. Second part is the power consumption. Power consumption is under root 3 BL IL cos phi. It is now 45,000 watt.